So we're going to continue with cryptography, and in particular we're going to now start looking at integrity. So far we looked at confidentiality, namely how to hide the contents of a message from people who are not supposed to see them. And now we're going to look at integrity, namely how to prevent attackers from modifying a message or claiming it comes from someone it doesn't come from. Is the sound good in the back? Is the sound good in the back? Okay, great. Making sure. Okay, so the first primitive we're learning about are cryptographic hash functions. So cryptographic hash functions. So a hash function is basically a deterministic function that takes an input of any size. This is what this star means. It means it's of any size. But it always maps it to a fixed size. So in this case, this hash function has L bits of output. Okay? So you can take any size of an input and it shrinks it down to L bits. For example, SHA-256 is a standard hash function used, cryptographic hash function used today, and it outputs 256 bits, no matter what the input size is. So it's important that it is deterministic. So it will always map a value to the same hash function. It's not like encryption, which we saw has to be randomized to in order to achieve in CPA. Hash functions are deterministic. Okay. So when you take the hash of a message X, we call this to be the hash of X, or we call it to be the digest of X, or fingerprint of X. Okay? So essentially, it's all the information about X condensed in a hash. Now, you won't necessarily be able to invert the hash function and get X back, but we'll see properties that it has, such as collision resistant, namely two different X's will have different hashes. The hashes won't be the same for two different messages. Okay, so like any other cryptographic scheme, it has properties such as correctness and security, and of course efficiency in terms of being able to actually compute it. So in terms of correctness, all that you need from a hash function is to be deterministic. So whenever you plug in X to H, you always get the same answer back. When it comes to efficiency, well, computing H should be easy. Should be easy, and by easy we mean polynomial time, but in practice, ideally, should actually be fast to compute a hash function. Now, in terms of security, we want a few more things. So for security, we want a property such as one-way, which we learned about already. Namely, an attacker should not be able to invert the hash function and obtain some X that matches that hash. We also want collision resistance, namely the attacker should not be able to find two X's that map to the same hash. So let's write them down. So one way. This one is also called pre-image resistance. Essentially because it's hard to find the pre-image. So given a hash, the pre-image X that led to that hash should be hard to find, so it's resistant to finding that pre-image. So basically for all adversaries, again, polynomial time, because that's the only thing we really consider in cryptography, then the probability that if you chose an X randomly, okay, so the $ means random, and you computed Y to be the hash of X, and you give it to the adversary, the fact that the adversary is able to produce X, this probability should be basically negligible. So a few questions here. One is, why did I say negligible and not 1/2 plus negligible as for in CPA? Any ideas? Why negligible instead of 1/2 plus negligible, as in the case of INCPA? Why am I not okay with 1/2 plus negligible here? Yeah?
Because we are not guessing between two options, but like random options, so there is no like one.
Exactly. It's because we're not trying to guess between two options, namely bit M0, namely whether message M0 or message M1 was encrypted. We're not trying to guess between two messages. We're trying to actually guess the whole value X here. And in particular, this negligible, you can think of it as being 1/2 to the size of, the output of H, right? So something like L. You can think in terms of that, right? So it's really it's 1 over an exponential. It's really negligible. Or you can think of it as 1/2 to the key K in INCPA. All right, so this is one-way function. And another question is, why was it important to choose X randomly? Why didn't I say for all adversaries, for all X's, the adversary cannot invert Y and produce X? Why is it important that an adversary cannot invert the hash of a random message? Why don't I just request that the adversary, for all X's, whatever their hash is, the adversary cannot produce X back? Basically, I'm saying, what if I had something like this? For all adversaries, for all X's, probability that if the adversary is given the hash of X to produce X should be negligible. Again, I don't want this, but why is this a definition that's actually not attainable? I cannot construct a hash function that will be one way in this way. So here's why, because I can just take a value, let's say take X equals 2, okay, whatever. I'm going to compute the hash of 2, right? And I'm already an adversary that if you give me hash of 2, I know it was 2. Okay, I'm already such an adversary that if you give me a hash of 2, I know it was 2, and this is supposed to hold for all X's. Okay, so that's why it's not attainable. You cannot construct such a hash function because, you have to be able to compute the hash function, so I can compute it on any one value, and automatically I know what's the preimage for that hash. Okay? But the point is that it's really hard to find the preimage when you choose an X at random and you compute its hash. Any question about this? Yeah, question? Yeah, I'll explain it again. So it's difficult to invert the hash if you're given the hash of a random X. Then it's difficult to compute that X. But it's not difficult to invert the hash for any X. Why? Because you can compute the hash for some X, right? Take value 2, compute its hash. So there you go. You know the inverse of the hash of 2. It's 2, right? So you can invert hash for some specific value because you computed the hash for that specific value. Okay? But for a random value, it's much harder, right? Because you're just giving the hash and you have no idea how to obtain the value that produced the hash. Okay. Now, the second and very important is collision resistance. And this is what cryptographic hash functions are primarily used for. So basically it says no human or human machine can find two X's that are different but mapped to the same hash. So it is infeasible to find X and X prime such that they are different and they hash to the same value. This is a collision. And the point is that you should not be able to find a collision in a hash function ever. So currently for SHA-256, we don't have any such collision known. Okay? So is assumed currently, because things change, to be collision resistant. Okay, and this is a standard hash function that's widely used today. So in 2017, we have something called SHA-1, which outputted had less bits, so the output of this one is 256. And it used to be that, the hash function that's used by default, but then Google, with its huge compute power, was able to find a collision. And Google produced 2 PDF documents that were hashing to the same value, so then people stopped using SHA-1 after that. And we changed to SHA-256, for which we don't yet have a collision. Okay. So basically a simple deterministic function that computes a checksum or a fingerprint of a message, but in a way that you won't have that fingerprint repeat for 2 messages that one can feasibly find. Now, a question is, if I give you a hash function that, let's take SHA-256. Do there exist collisions in SHA-256, or is it possible to not even have collisions exist? Yeah? Yeah. So SHA-256 has a ton of collisions, infinite amount of collisions, but we just can't find them. Why? Here's why. Well, you see, you can map a message of any length to 256-bit space. So in particular, you can map, messages of 1,000 bits to a space of 256. How many of these are there? They're 2 to the 1,000. And you're mapping them all to 2 to the 156. Okay, so there's going to be lots of collisions. There are a lot of collisions. It's just that we, humans and our machines, cannot find them. Cannot find even one of them. So that's basically the assumption on the cryptographic hash functions. And people have ways, mechanisms to build confidence in a hash function that it's collision resistant. They run all sorts of tests and certain techniques. They make sure that they don't work. But ultimately, it's an assumption because there are collisions.